today. In behalf of the University of Texas Tyler, we're glad that you can make it. We are streaming live also for Tyler. And we have the first group today is actually group 9. They are going to be presenting basically what they have done for the last 2 semesters. And welcome group 9.
Thank you.
Thank you.
Whenever you guys are ready, please feel free to start.
Good morning again. Thank you everyone for being here with us, group 9. Today we're going to go ahead and introduce you guys our design, which is a moped lift. My name is Dauda Moped. To my left I have Raif Montero, Mazhan, and Jake Simeon. A moped is a motorized bicycle with low speed with pedals. And to get us started, I'm going to have Raif go ahead and step up.
I'm going to go over our project justification. So at the start of any project, you want to start by justifying why you were designing your product in the first place. So we started off by researching, is there any moped lifts on the market, and what is the market for these lifts? So what we found was that there aren't actually any moped lifts on the market, and that there is quite a large market for mopeds worldwide. So in the US, there was 220,000 units sold in 2008, and there's a projected market of 71 million units globally. This can be explained by the need for more fuel-efficient vehicles as population density and population goes up.
Some of our initial design goals was to lift up the moped safely, because that is the main thing we were looking for. Also providing an ease to lifting it up, and then also providing a safe, efficient, space-efficient solution for moped lifting. By doing that, we use our motorcycle lift as a benchmark for creating our moped lift.
Once we had our design goals in mind for our project, we began brainstorming potential solutions to our problem. First thing we came up with was a pulley and metal cable solution that would allow the user maximum adjustability. However, once a torque was applied to this suspended load, it could result in slack in the cables, which would be a risk to the user. Secondly, we decided to come up with both horizontal and vertically mounted hydraulics to position the lift, but this resulted in difficulties with the suspended hydraulic using its force. Finally, we came up with a gear train rotation, where the gears would reduce the torque necessary to rotate the load so the user could crank and rotate the bike about its axis.
Some of our initial specifications, including was to lift up a 200-pound load. Our moped was 130 pounds. We did a factor of safety for 1.5, so it came to a 200-pound load. We decided to lift it up to 2 feet, which is usually, we chose that height because that's usually the lifting of a bike lift usually are built to. And then we decided to rotate it to a 180-degree angle, which means 90 degrees towards the right and 90 degrees towards the left, and then safely locking the mechanism.
And here we have one of the many sketches we did during the process. On this sketch, we have the back side of our design. As you can see, we have the gear train. We have the plate that the gear train is sitting on. We also have some of the dimensions, like the lifting dimension. At first, like I said, we did it to 2 feet, but we were thinking between 2 and 3. Maximum rotation, even though he said 90, just like Matt just mentioned, we say 90 on each side. We figured tilting it at a 45-degree angle is the same as tilting it at 90, because you'll be able to have access to the motor and everything else. We have the ram, which is the hydraulic pneumatic ram. And on the bottom, we have the wheel just to be able.
Next, we started off by making a prototype so we can solidify some of our basic design components and some of our concepts. It's made out of a balsa wood and balsa wood construction and uses syringes in the form of the ram. Over here you can see the side and front view of our construction. What this prototype taught us is that we actually needed to widen our base to accommodate our moped possibly tipping during loading and forward and side to side.
And here we have 2 of the 27 CAD drawing that was done on AutoCAD Inventor. On the right, we have the C channel, which the gear train was mounted on different views. And on the left, we have the rotational assembly. We have the back view, side view, and the front view.
Once we had a design secured for our lift, we decided to go ahead and use Autodesk Inventor to run an FEA analysis to ensure the safety of our frame. This FEA analysis was done with a max lift height as well as the max lift capacity and the maximum rotation on our lift. This would hopefully yield the maximum stress value so we can ensure that the maximum load is capable of handling. As you can see from this picture, the first picture is the entire lift with the FEA analysis, and the second is a zoom in of the highest point of stress, which is on the rotation axis as we predicted. This maximum value is 29 KSI, which is comparable to, 26 KSI, comparable to the yield strength of steel at around 30 KSI. So we shouldn't be experiencing any permanent deformation of our lift. This one is the deformation, which occurs maximum at the end of the forks of our lift, as kind of expected, but this deformation is less than an inch.
Testing. When we get to overtexting, we noticed that after applying the load, the members were flexing. They were not stable enough. Second of all, the position of our telescope assembly was causing the position of our ramp was causing our telescope assembly to cock a little bit. And then we also noticed that our stand was not rigid enough to provide the support that we were looking for. Therefore, in the front of the bike also, we was struggling by itself to leave the ground.
After some testing, we decided to begin to evolve our design to try and combat some of the issues we were experiencing. Firstly, we realized that, as Dow previously mentioned, the max rotation of 180 degrees was a little overkill, as you were granted equal accessibility with only 90 degrees rotation, with much less of a torque requirement on the axis. Secondly, actually increases the maximum lift height, so we didn't need the depth benchmark of 2 feet, and we decided to instead go with 1.5 feet. Next, we decided that the gripping mechanism to grip the bike, it actually gripped the kickstand of the bike, and this wasn't as secure as we were hoping it would be. It worked, but we were looking for a little more rigidity, so we adapted it to brace the frame of the moped instead. Here you can see the original design. Oh, sorry, this is the original design of the kickstand. As you can see, there's room for the bike to slip within the adaptation. Second one is, as you can see, it's sandwiched both vertically and horizontally around the frame, which was much more rigid and provided much more structural integrity.
As you can see from the picture shown, we added reinforcements to our main structure in the form of an angled beam on the side connecting the outer telescoping arm to the main bay, as well as members interconnecting the legs and the main base to add safer and more sturdier design. The upside to these members is that we were able to actually reposition our ram to the middle. So we're actually able to add an extra leg at the bottom to facilitate the ram having a sturdy position during operation. In this picture, you can actually see our initial ram position was right here and was connected via these jutting out angle irons connected via this rod right here. When it would come up, our telescoping assembly, when it was at max height, was causing the telescoping assembly to move forward. So by positioning our ram right here, we were able to support the load directly where the load was.
And the last thing that was added to our process was the right edge stripe. The stripe was added because as we lift our bike and try to rotate it, we wanted to make sure that the front of the bike is going to be lifting at the same time as the rest of the load. Also, we wanted to keep the bike handles straight as we do the whole rotation going to the left or coming back to the right. We wanted to keep the whole handle straight as we do that. Final design specification. So for our final design, we decided to go with the hydraulic pneumatic lift to be able to lift the 200-pound load. We did the gear train rotation going towards left and right, and then for our frame, we just built our frame using radial steel to build our frame.
As you can see, this is our final product on our Autodesk Inventor. When the lift is fully up, this is the picture. This is the complete assembly of the lift. And this is the side view of the lift. That was the original position of our ramp, and we moved it in the middle, as you can see right here. This is the actual product when fully completely built. When it's extended, it's 64 inches by 4 feet long, and when it's put back like to store, it's 25 inches by 4 feet. We chose these dimensions because this we think is the ideal size for anyone to store in their garages without having to moving their stuff around.
Once we had a final design for our build, we decided we need to validate a lot of the components and make sure there will be no yielding present. As you saw previously, the steel frame was up to safety specifications as the steel wouldn't yield. We additionally calculated the weight on both the bearings and the ram to make sure that they were rated high enough for the load. We then used a torque reduction through the gear train equation. First found the max torque divided by the gear ratio to eventually yield a maximum user input of less than 45 pounds, which a right human strength study showed is easily output by any healthy adult. Finally, we had to create some tipping boundary conditions to ensure that the base wouldn't cause the lift to tip under the load. Here we can see two pictures. The first one is the front view and the second is the side view. On these pictures, the red lines represent the center of gravity of the load, and the green lines represent the boundary in which the red line must remain to avoid tipping. Even with this exaggerated rotation of a full 90 degrees, we can see that the boundary still remains within the green lines.
Next, I'm going to demonstrate that the versatility of our lift allows the user to load the moped in either the forward or backward position for any desired maintenance that they require. Next, I'm going to go over the operation video of our lift in action. So right here you can see I'm actuating our ram via the pneumatic feature. We chose this pneumatic feature because we felt like it would give the user the ability to fine-tune their adjustment, and compared to the manual way of just cranking it, it also makes it cooler. Also, which is about to come up, when I rotate it, this rotation is accomplished via this winch that we integrated into our design. This winch actually has a locking paw that allows the user to lock it in either direction, and also has a free spin portion of the lock. Another upside of this gear train is it actually reduces the overall force that the user will need to actually rotate their load. Instead of just having one gear or just a cylinder rotating and another cylinder, we have these gears reducing the force. Lastly, which is about to come up in the video, is it shows how easily these legs are to be brought up and brought down with these pins and locks that we designed. As you can see, we had some kind of jiggling here and there. We weren't too worried about that because it was just due to the fact that our rotational assembly is kind of small. We did reinforce it, and it did reduce some of the shaking. And yes, like I was saying, these are the legs being retracted. It's easier to pop the locks in and out and just bring them up and store away.
So after we build our prototype, going through the cost of our prototype, material, we use about $520 material. Labor, we weren't sure exactly how to go and calculate labor, so we just average at $30 an hour, which come out to $1,800. So if you want to do a mass production of 1,000 units, and the cost will go down from $520 to $375. If you were to resell it at the price of $575 for each unit, we're looking at a profit of 55%. In conclusion, we designed our lift and we built it. The design came out right, and the prototype was tested and validated, proving the economic feasibility was also proven to be right.
Lastly, after we finally finalized our final prototype, we came up with a list of further improvements or considerations we would make on further prototype iterations. One such change was changing these our torque arm to be brought in more, and it would also cause the ram to be brought in more, so we would have less forward torque, and the load wouldn't shake as much, and it would just be more sturdy, streamlined, and concise. Next, I would honestly add some locking wheels to the base, because during rotation you have some shifting of the load and stuff. It wasn't too bad, but it is a necessary improvement. Other future considerations, would be the use of ATVs, larger motorcycles or small vehicles, granted that we added a mirror image of our lift on the other side. This would give it increase its structural integrity and also increase its load capacity. Due to the adjustability of our lift, we could add holes here, and we could add holes here for locking the telescoping when it's at its max load. And then also we could adjust this depending on what you're lifting, what height that's at, and how to, and so we can actually make interfaces for these ATVs, motorcycles, and small cars because of the adjustability of our lift.
Finally, we want to thank you guys for our senior design presentation. We want to thank Dr. Garcia for wonderful ideas, and also Ray's brother shop, Select Motorworks, for letting us build this wonderful thing. Questions?
I got a question.
Yes.
First off, I want to say, wonderful outfit. This was my partner a few years ago. We had a group and we had the exact same outfit.
Okay.
Every single presentation, no matter if it was formal or not. So I appreciate that as well.
Thank you.
One of the questions I have is material selection. So which steel is this? Is this 4140 or C300? I didn't really.
It is 4140.
It's 4140 still. Any particular reason why you decided to go with that?
It's commercially available and cheap.
Okay. And another one of my questions is, you said if you were to mass produce this unit at 1,000 units, it'd be around $375, right, per unit?
Yes.
How long would it take to actually manufacture those units? Like, what's the fastest turnaround?
We were assuming with the adequate shop that they could probably build this in 3 hours because it doesn't require too much. It's just some holes, some cutting, there's no tube. The tolerances aren't that crazy and the material's pretty easy to fabricate, and none of the things that we design are too hard to fabricate to begin with. So yeah, you just pop them out.
Yeah, and the cost of our labor, as you can see, is a little high. Like you said, we did, the shop we used was not a perfect shop.
Okay.
So you kind of make the cost a little bit higher. But yeah, like you said, anything under 3 hours.
Yes, just a basic question from the beginning. You know, I'm not familiar with motorcycle lifts and moped lifts, and that's not my forte. But when you're presenting to somebody who maybe doesn't necessarily have a whole lot of background in this, one thing I didn't walk away knowing was what about motorcycle lifts does not work with mopeds, and what solution does this lift address that is not addressed by existing lifts?
Well, most existing lifts on the market are actually just a simple scissor lift with a tray on top of them. So while there's no reason that a moped couldn't specifically be used with one of those, we wanted to add the addition of rotation, and we specified it for a moped because it was a much more reasonable load to handle for a prototype. Although, as was mentioned previously, we would like to adapt it so that we could perhaps use larger motorcycles and still have the addition of rotation there.
Motorcycles are usually operated and fixed nowadays from the top, but moped is still old school. We're looking at 50 past years in third world countries, so they need a permanent solution for that. So that's
with the aspect that Jake was saying about the scissor lift, lifting it from the bottom, that actually restricts the user from maintaining anything from the bottom of the bike. So we wanted to get rid of that design altogether. We wanted to free up the whole bottom of the bike to be able to maintenance, and by rotating it, get to that area easily.
Yeah. Well, I want to thank you for your presentation and for the work that you have done here. I think it's excellent that you've been able to build this. I can't build anything, even if I have instructions. But one of the things that I want to address is that, like her, I'm not familiar with motorcycles, right? I did have a scooter when I was in college, and that was about it. So one of the things I'm struggling to understand is what need are you trying to solve in the market? Let's start there. And really, why do I need to lift my moped from the ground?
Yeah.
Okay. So, so for the need, as Jack mentioned already, on the second slide, there was 228,000 mopeds sold in the U.S. With the projection by 2020, it's going to be 71 million worldwide. So that's a big market to target. And like he mentioned, the bicycles, most of the bicycle lifts, they just go across and go up.
Yeah.
So to work on them, most of the mopeds, the motor is on the side.
Yeah.
So to be able to get to the side without having to completely have the moped on the ground, where you can just tilt it at a 45-degree angle and just work on it. So that's.
It's a little more of an ergonomic
And then, for
solution.
example, changing a tire, you don't need another person to help you with it. You can just use this lift and, for example, to change the tire or check if there's a puncture or something, you can just do all of that by yourself without asking anybody's help if you don't have it, for instance.
So the solution that you're trying to provide is so that I can do it myself
Yes.
without need or
Without
help
anybody
from
else's
anybody
need,
else.
yes.
That's something important to highlight. And then the other thing is related to your cost, right? So you're saying that you can sell it for about $500 or so.
Yes.
I'm not sure how much is a moped. Last time I had my scooter was probably like $400. So what makes me want to buy a prototype that's gonna lift it, that's almost as expensive as my motorcycle or my moped?
Okay, on the market right now, the average price for any lift is around between $400 and $600. And like you say, it is $575, but it's not a one-time use. I mean, you use it eventually, for the longest duration that you keep your moped. And like you said, we were targeting third world country. Moped might not be something big here, but in a lot of third world country, they do use moped as a form of transportation.
But they also have less money.
Yeah, they do.
Again, it was kind of a proof of concept to potentially adapt for motorcycles, so a shop could buy it, or anyone with a higher, what would you call it? A higher budget.
Sure.
Say a Harley Davidson user, much more money to kind of throw around, if you will, could easily afford one of these and be
Yeah.
able to maintain it alone.
Yeah, this product would actually probably do better in a maintenance shop or so, or it could be sold to like a diehard do-it-yourselfer that wants a lift.
Yeah, you guys know me, I rode all the time, and I think it's awesome.
Yes,
If
thank
it
you.
was applied for a motorcycle, and I had that in my garage, it would make a lot of the work that I did way easier.
Yes,
And I
yes.
think you guys are headed in a pretty cool direction.
Thank you for that.
No, something that I believe, and from the two questions that came, is that maybe being a little more upfront on the end user. The end user will be actually owner of the bike, or it will be for every technician to have access to with a single mechanic having the opportunity to do it without having to have more people or more help in the shop. Things to structure more.
I actually wanted to make a quick point on the further adaptations for doing ATVs, motorcycles and such. By adding a mirror image and taking these legs off and just keeping the whole thing, these legs would actually fit into the other slots of the mirror image. And then obviously the other mirror image would have this fork or this T and fork, and those would interconnect. So it actually, be easy to, make it happen. There wouldn't be that many changes that would have to take place. Yes,
One question I had was on your factor of safety. What was your factor of safety?
1.5.
1.5. Where did you get that?
Well, our Vespa, which we used for testing, was 130 pounds dry weight. So we got 200 pounds for the factor of safety.
Okay, because in my past experience, when I've done lift designs, now it's a little bit different than garage things,
Right.
but when I've designed, lifting lugs and things like that, I typically have seen factors of safety way higher than that, like 5, maybe even 10. I mean, you're gonna have somebody underneath this thing.
Yeah.
For the majority of the structure, the factor of safety was actually much closer to 15. It was only the minimum factor of safety was around 1.5, but
Well-
we would aim to increase that later on.
Your factor of safety is your minimum. I don't care if there's some component somewhere that can handle
Right,
15. It's the chain weakest link effect. So
Agreed, yeah.
your factor of safety is only 1.5. That does concern me, especially if you're. If you're marketing this to a home gamer, somebody who's going to be having this in their garage. I mean, what happens if they have this in their garage, you're working on this, and then your your 10-year-old comes in from the house, leans on it.
It is obviously something that would need to be addressed in further
So
iterations.
I would encourage you to look at a larger factor of safety and also consider alternate loadings, like different loadings. So yeah, maybe you know not to lean on the thing.
Yeah.
But what happens, again, what happens if the toddler comes in? What happens if the 10-year-old comes in? You're advertising this to people in their homes. And so you're going to get people, what happens if there's somebody who's had 3 beers and they're working on it and then they lean on it and then it falls on them? Well, you're getting sued even if they were a little bit, tipsy that day. So I would encourage you to look at both a higher factor of safety and different loadings beyond your basic loading case.
Absolutely.
Basically think, what happens if somebody sits on this or leans on this at random locations?
Right, absolutely.
Any more questions?
Anyone else? Well, to thank again.